Hello. Um, we are moving on to memory today, and we're going to be looking at the first of the models for memory. We're going to be looking at multi-store model of memory. Might be quite a long one. There's a lot of pieces of research for this that you do need to know, but none are named in the spec, which means that you only need to really know what that piece of research found rather than the whole sample, procedure, conclusion, aim, bollocks. So consider the following question, right? We're starting to look at memory. Memory is this really, really, really complex thing. It's a little bit dry in places, right? It's not the sexiest topic that we look at. But consider this question: why would it not make evolutionary sense for all of our memory to be stored in one part of our brain? And by extension, why does it make more sense to have multiple stores of memory in different locations in the brain? I think the answer is quite obvious here. The obvious answer is because if we get hit in the head or we have a stroke or something and it hits our memory and all of our eggs are in one basket, all of our memories are in one place, our quality of life disappears instantly. We would not be able to remember anything. We would not know the names of anything. We would not be able to talk, honestly. So from an evolutionary point of view, what we have done is we have put our memories in different locations. And what we are looking at here is the multi-store model of memory, right? The name kind of gives it away. So Atkinson and Shiffrin are who created the model back in the late 60s. And they kind of come up with this idea that we have three different stores in our brains, four different parts of memory, four different types of memory. And each of these stores has different codings, durations, and capacities. And yes, you do need to know the codings, durations, and capacities for each. But you also need to know what they are. So capacity is how much information can be retained. So for example, if you think about the capacity of a stadium, for example, the capacity deals with how much that can hold, how much that stadium can hold, how much that store can hold. You've got duration, how long can the store retain it for? And again, you need to know the duration for all three stages. And you also have encoding, also known as coding, the form in which the memory is retained. Bit like qualitative, quantitative, data can come in different forms. Memories can come in different forms as well. So this is the memory. This is the multi-store model. Firstly, please make a note. This is a model of memory. It's an inference. INFERENCE. It is an inference. It is an educated guess about what memory looks like based on research because we cannot physically observe this. So the idea, by the way, is that we have environmental stimuli. I'm going to use my pen for this, actually. There we go. So we have environmental stimuli. This is the things that come into our five senses. So right now, there's a lot going into all five of your senses, and that is being put in the sensory memory. Now, this holds all your memories from all this information from your senses. Anything you are not paying attention to, is being deleted immediately. Anything you are paying attention to is going into your short-term memory. So, for example, you've got a lot of information coming into your senses right now. But hopefully you are paying attention to your auditory information. So I'm hoping you are paying attention to me and my voice is being moved immediately from the sensory memory into the short-term memory. Everything else, the feel of the clothes on your skin, for example, the temperature of the room, you are not paying attention to these things, and thus that memory is being deleted immediately. So we move whatever we're paying attention to from our short-term memory onto our long-term memory, essentially. Fine. And then it will enter into our short-term memory. A couple of things. I'm going to go back to sensory. Actually, no, I won't. No, it won't. No, it won't. Short-term memory is very short, 18 to 30 seconds long. If you want to get something onto your long-term memory, if you want to get something onto there, you have to elaborately rehearse it. As in, you have to go over it, 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 until your brain recognizes that it is quite important. What you can do is, if you're not moving on in that way, because the short-term memory is very brief. Memory in our short-term memory decays very, very quickly. We can maintain it by just rehearsing it. Essentially, we can go over it again and again and again. Just rehearse it, and that is the absolute very basics of multi-store model. Just note as well, when we retrieve information, as you can see coming from our long-term memory, we are retrieving it into our short-term memory. Fine. Let's go through them individually. Oh, whoopsies. So let's start with sensory memory in a bit more detail. It's based on your 5 senses. And here we go. A lot of information here. The sensory stores are constantly receiving information, but most of this gets no attention. The incoming data remains in your sensory store for 2 seconds at most. Now, that's the duration, and you need to make a note of that. The duration of sensory memory is 2 seconds. The capacity is incredibly large. You have an incredibly large amount of information going into all 5 of your senses right now. If you just take sight alone, I'm looking around my classroom, there's so much data that's going into my system. There's so much stimuli that's going into my system. All 27 chairs, all 27 tables, the carpet, the plants, the walls, the whiteboards, everything. And then students on top of that as well. I mean, there's no students here now, but you take in a hell of a lot of information from your 5 senses. So the capacity is very, very big. The encoding is probably best just to put sense specific. So we store auditory information, auditorily, for example. We store visual information, I don't know, maybe visually. So encoding is a bit of a difficult one here. You do need to know a piece of research for sensory memory. Sensory memory is very quick. You know, if you look up at a light, stare at a light, stare at a light, stare at a light, then close your eyes, and you're left with that buggy light thing that moves around in your eyes. That's sensory memory. Sperling wanted to test specifically the duration, not the capacity, not the coding. They wanted to test the duration of sensory memory. And they basically showed participants a 4x3 grid of letters like the one on the screen. And they would expose it for 50 milliseconds. So this would flash up 50 milliseconds. And then they were asked to write the whole thing. Recall was quite poor. People could remember if it was one line, but by the time, F, C, H, D, by the time they got to D, J, R, P, O had decayed to the point where they couldn't remember it. The point here is sensory memory is incredibly brief. It's really, really brief. If you're not paying attention to it, it gets deleted almost immediately. So this demonstrates how information can decay very, very rapidly. So you need to know sensory memory, and you need to know one piece of research for sensory memory. It's the same sort of thing for short-term memory now. So short-term memory is pretty much anything in your immediate past, i.e. the last 30 seconds. Your short-term memory generally lasts a maximum of around 30 seconds. 18 if you have a particularly bad memory. So short-term memory holds information in a very, very fragile state. You can hold it for longer than the sensory memory, but it decays very, very quickly unless you start paying attention to it, rehearsing it. And then eventually it will go into the long-term memory. So it decays very, very briefly if not paying attention to. And it doesn't hold that much. So not only does it decay very quickly, but it doesn't actually hold that much. You can hold up to 9 items in your short-term memory. And then any more comes in, you will lose some of the older information. It gets pushed out. So, for example, someone comes up to you in a club and wants to give you their 11-digit phone number. And they start going, oh, you're very attractive, oh, love me or whatever. Here's my number, 07590836241. You wouldn't be able to remember all of that because that's 11 digits. Your short-term memory is only 9. You remember maybe 075908662, and then you wouldn't be able to remember anymore. So you'd have to get her to repeat it or get them to repeat it over and over again. Basically, short-term memory has a limited capacity, right? In terms of capacity, again, you need to know research. What I've got here, by the way, is I've got research for capacity, but I've also got research for duration as well. So I'm going to go through the capacity, and you're looking at Jacobs. Now, Jacobs, that is a true year, by the way, 1887, one of the first psychological experiments ever done. This is how important memory is. But they basically tried to get into people to remember as many digits or items, like letters, for example, as they possibly could. And what they found was they could remember 9.3 digits. So like numbers, for example, they could remember 9.3 digits on average, where it was 7.34 letters. So numbers are easier to remember than letters, but both of them demonstrate that actually short-term memory is actually quite limited. Miller is also something you do need to know. Miller is 1956, came up with the magic number 7 plus or minus 2. So 7 plus or minus 2. That's the best way to describe capacity of short-term memory is 7 plus or minus 2. Okay. What that means, by the way, is most people fall between 5 and 9. 7 plus or minus 2 is basically 5 to 9. People will remember 5 to 9 items. If you've got quite a bad memory, for example, you're probably only able to remember probably 5 digits. Yeah. That's not a lot of information you can hold in your head. Okay. Chunking is quite important, though. I would go more over this in class, but chunking is a practical application of everything we've looked at so far. And it's basically the idea that if you can remember 9 digits, what happens if you paired up some of those digits? So instead of remembering 5, 6, 2, 1, why not remember 5621? You're chunking them together, and 56 would be counted as one digit. 56 would be counted as one number. So why not combine them all? And actually, it has been found that if you chunk information, you can remember it a lot more meaningfully. Fine, right? Let's go into a piece of research about duration. And the main one you need to know is Peterson and Peterson. So what they did, they were husband and wife team. They tested for how long short-term memory is by giving people a nonsense trigram. That's what they called it. They'd give someone something like this: 3 letters followed by 3 numbers. Fine. And what you had to do is immediately after hearing the syllables and the numbers and the digits, the participants were asked to call backwards in 3s or 4s from this number. Okay. And then afterwards, they were asked to recall the consonant syllables, the letters. So if I were to go 303, going backwards in 3, right, they say WRT 303, and I go, right, 300, 297, 294, 291, 288, 285, 282, 279, 276, 273, 27, and at some point they'll go, right, stop. What was the 3 number? What was the 3 digits? What were the 3 letters? And you have to remember. Now think about what I'm doing as I'm counting backwards. It takes all of my attention, all of my ability to rehearse, and that puts it on the numbers. So if I'm counting backwards, I can't repeat this. I can't rehearse this. And slowly that information is decaying. That WRT is, as I'm going backwards, 291, 288, 285, 282, 279. As I'm going backwards, this is slowly decaying. And doing this tons and tons of times, you can basically figure out what the mean average of short-term memory is. Short-term memory is somewhere largely, I'm very tired today. It's somewhere largely between 18 and 30 seconds. So that is what you need to know for this. And that was found by Peterson and Peterson. And you have all the short-term encoding duration capacities there as well. And finally, well, not finally, not quite. You do need to know a little bit about this moving from short-term memory to long-term memory. So if I scroll backwards, if I go back to the beginning of the slides again, I get back to this. And as you can see, moving from short-term memory into long-term memory is done by elaborative rehearsal. But you do need to understand that this goes wrong in some people. And there are a few case studies, which we'll go through later, but there are a few case studies in which people have broken that ability. So initially, rehearsal maintains information in short-term memory, right? But you need to, that's pretty gone for it anyway, that's fine. Clive Wearing is a good case study. Clive Wearing was a talented piano player, or pianist, who had a stroke that was caused by, I think it was a variant of the herpes virus or something. But he had a stroke in a very, very particular part of his brain that doesn't usually see that much strokes. So your vision sees strokes quite a bit, but this part of the brain doesn't. And what this part of the brain was responsible for was the moving of information from short-term memory to long-term memory. After the stroke, he kept all of his long-term memories from before the stroke, but he was unable to make new memories. So he basically lived in his short-term memory. So he would keep forgetting things after 7 seconds and had no idea where he was. Every 7 to 30 seconds, his short-term memory, right, so it's usually 18 to 30, but because of his stroke, he was a bit all over the place. He would not remember anything, and his wife would go out and make a cup of tea. She'd come back in again, and he thought he hadn't seen her for like 30 years. And I will show you a video. It's quite an old video now, but and she's left him. So I think he's still alive at the time of filming. He must be about 70, 80 now. But Clive Wearing is the case study you do need to know. He can play the piano like no one's watching. His piano skills are incredible. But making new memories? No. Now, what you need to know about Clive Wearing, he is case study evidence. So it's just one person backing up a whole model. He is case study evidence that we do have multiple stores of memory, because he's had a stroke and one form of his memory is affected, but not the other, not long-term memory. So it's pretty good evidence that memory is actually in multiple stores. Okay, and then finally, long-term memory, right? Long-term memory, you need to know Baric. I don't know if this is on here. No, it's not. But if I were to say the capacity for memory is long-term memory is massive. So again, you need to note that down. Capacity for long-term memory is massive. The duration is potentially forever. Duration is potentially forever. And then the encoding for long-term memory is somatic. We encode long-term memories with meaning. It helps us understand something. If you do not understand this theory, and you do not understand the meaning of this theory, and you might know it, but you don't understand it, it will not fit in your long-term memory. So in order for something to fit into your long-term memory, we try to attach meaning to it. So Baric looked at the duration, and this supposedly forever, like it's long-term memory is supposed to last forever, kind of rubbish. So this is what people know, or my second years know, as the yearbook study. The yearbook study was basically he gathered people who had left college 15 years before, or less than 15 years before, and he gathered people that had left like 48 years. They were like 64 years old. And he basically showed them their yearbook. Now, if you have a look, if you've left within 15 years, apparently you can remember up to 90% of names or faces. That's quite strong. That shows you that long-term memory is actually quite effective, to be honest with you. But if you add another 33 years onto those 15 years and you get people that left 48 years ago, it does go down a little bit, but the fact it doesn't go down that much is a testament to how good your memory is. It declined to about, people could remember 80% of names and 80% of faces. So sometimes they would just show the face and you had to guess the name. Sometimes they would give you a name and you had to pick a face out, for example. So it highlights the foreverness of long-term memory, right? Your long-term memory is incredible. If you can, and the way to phrase this, if you can remember anything that happened more than 30 seconds ago, okay, and you can remember it more than 30 seconds ago, it's in your long-term memory where it will last forever. Just because you can't remember what I'm thinking about in the next year or so doesn't mean it's not there. So there are a couple of further pieces of research, right? If you want to use this, feel free to do so. Everyone's going to go for Baric. So if you want to make yourself stand out, you probably want to look at Baddeley's memory. He's going to come up a lot, by the way. Baddeley's going to come up a lot over the next couple of weeks. There is also evidence that brain scans are demonstrating that you will almost getting to the point now where we can literally see the different stores in the brain. So this right here is the prefrontal cortex. It's the front part of the brain. So the front part of the brain seems to be active when we use our short-term memory. If I throw something out to you, like a new bit of information that goes to your short-term memory, your front lights up like a Christmas tree during that point, because this is our processor right in the front of our head. This is our processor, and it only lasts 30 seconds. The hippocampus, which is right in the middle, the hippocampus is about location memory. If I get you to close your eyes and describe your house to me whilst you're sitting in the classroom, what's happening is this little bit just here is lighting up again like a Christmas tree. So the hippocampus does seem to be active, particularly when we do memory, like long-term memory locations. If I ask you to get you to plot your route in your head, you leave your house and walk to your primary school, that would be your hippocampus would be involved there. No HM. You need to know Clive Wearing, 100%, but you do need to know HM. Definitely need to know HM. And I'm not going to go into too much detail about that. So as always, there are a couple of additional bits here in terms of evaluations. We've not really looked at a model yet. So the problem with this one to begin with is that it doesn't really go into how the memories work. And this kind of leads into the second point. This model only really talks about structure of memory, what it looks like. It does not go into a grand amount of detail about how it works. So therefore, it's quite low in explanatory power. What is a consequence of it not being able to explain this? It's quite low in explanatory power. What we mean by that, it fails to fully explain the phenomena that it is trying to talk about. It's also quite simple. Do we really think memory is just split into 3 little boxes and we have these 3 boxes in different parts of our head? It probably is a lot more complicated than that. So what you could argue here, and I don't really want to go into this too much unless you're a second year, rewatching this from the first year, because it's a simple model, the model is mechanically reductionist. What I mean by that, it's reducing a very complex behavior down to a simple model, a simplified model of how it looks, which is probably not accurate. However, and I've slagged it off to high heaven here so far, but a good strength for this is that it is actually backed up. So I do have an elaboration just here. This again, I'm hoping you're getting to the point now where you're starting to understand how to peel right. Second year is not about what you write. It really, really is about how you write it. So we need to understand the structure as soon as possible. The point here, the MSN could be criticized for being too simplistic. Boom, done. Now elaborate. Why is that bad? Well, it's problematic because if the model does not represent the complexity of memory, the multi-store model could be considered to be mechanically reductionist and also invalid. If it doesn't explain what it's trying to explain, then it's not accurate. It's not valid. Where's the evidence for this? I could be bullshitting at this point. Wow. For example, the multi-store model only superficially describes the structure of memory and what it looked like, and it neglects to consider how these stores interact in any great detail. Now, I've not given any pieces of research for this evidence, but that's not what evidence means. Evidence doesn't mean you always have to give research. It could just be backing up your point with logical points. Therefore, it's considered too simplistic to adequately explain memory and its multiple stores. In terms of questions, you're highly likely going to get a question on this. It's one of AQA's favorite points to ask about multi-store model because they feel students don't really know about it that much. As always, I hope this is useful. On my slides, listen to the voice notes because I believe they go into a little bit more detail about each of the points, and you can find these on the slides. Peace out.